Hey everyone! Today we're going to talk about the invisible glue that holds pretty much the entire universe together. Yep, we're diving into the chemistry of connection, a super simple guide to chemical bonds.
So let's start with something kind of weird. Have you ever actually thought about why you can't just walk through a wall? I mean, we all learn that atoms are mostly empty space, right? So what's stopping you?
Well, the answer is pretty mind-blowing. It's all because of these incredibly powerful, invisible forces that act like a kind of cosmic superglue. They hold literally everything together, from the phone in your hand to the air you're breathing.
Okay, so here's our game plan. First, we'll figure out what a chemical bond even is. Then, we'll get into the two main ways atoms connect. It's all about giving versus sharing. After that, we'll check out the rules that make them do it, see what cool stuff they build, and finally, wrap up with why any of this matters to you.
All right, first up, what exactly is a chemical bond? Let's talk about this superglue. Believe it or not, it's this simple. A bond is just the force that holds atoms together. That's it. That is the force that keeps you from falling through the floor or walking through walls. Anytime atoms team up to make something, a chemical bond is what's holding them together. Okay, so if a bond holds atoms together, how? How do they actually do it? Well, it all comes down to their electrons. And really, atoms only have two main moves. They either give electrons away or they share them. And this chart breaks it down perfectly. Over on the left, we have ionic bonds. The best way to think about these is give and take. You've got a metal atom that gives an electron to a nonmetal atom. The classic example is plain old table salt. Then on the right, you've got covalent bonds. This is all about teamwork. Two nonmetals get together and decide to share their electrons. And the most famous example of that, you guessed it, water. So let's zoom in on that first one, ionic bonds. An electron literally jumps from a metal over to a nonmetal. The second that happens, they aren't neutral anymore. They become something called ions, which is just a fancy word for an atom that has a positive or a negative charge. And what do we know about positive and negative? Opposites attract. The story of salt is the perfect example. Look here. You've got sodium, a metal, and it has one electron it would just love to get rid of. Then you have chlorine, a nonmetal, that really wants to grab one more electron. So sodium gives its electron to chlorine. Now sodium is a positive ion and chlorine is a negative one. And bam! That attraction between them is what makes the salt you put on your fries.
Okay, so what about the other way atoms can connect? Well, that brings us to covalent bonds. This is what happens when two nonmetals get together. Instead of one just taking an electron from the other, they work out a deal to share. It's a real partnership.
Now, in this world of sharing, there are a few terms to know. The electrons that are actually being shared are called bonding pairs. They're the ones in the middle of the action. But some electrons just hang out on the atom and don't join in. We call those lone pairs. And get this, some atoms are so friendly they even bond with themselves, like the oxygen you breathe. We call those diatomic molecules. The sharing can get pretty serious too. A double bond is when they share 4 electrons, and a triple bond is a whopping 6.
So this begs a pretty big question, right? Why? Why does one atom give and another one share? What makes them decide? Well, it all comes down to the rules of attraction. Here is the one big idea that explains pretty much everything. It's a long word, electronegativity, but the idea is actually super easy. Just picture a game of tug-of-war, but for electrons. Electronegativity is just how strong an atom's pulling power is. Some atoms are super strong, and some are not so much.
So yeah, that's the official definition. Electronegativity is just how good an atom is at pulling electrons towards itself. And this one idea explains it all. If you have one atom with a super strong pull and one with a really weak pull, what happens? The strong one just rips the electron away. That's an ionic bond. But what if two atoms have about the same pulling power? Well, it's a tie. Neither one can win, so they have to share. And that, my friends, is a covalent bond.
A couple of other quick terms help with this. Electron affinity is basically a measure of how happy an atom gets when it grabs a new electron. And electrostatic attraction sounds complicated, but it's just the sciencey name for that opposites attract force we talked about, the one that glues those positive and negative ions together. Okay, so we've got the rules down. Now let's see what these bonds actually build. How do we go from these little invisible deals between atoms to things we can actually see and touch, like salt crystals?
When you have an ionic compound like salt, all those positive and negative ions don't just clump together randomly. They build this amazing, perfectly organized 3D pattern called a crystal lattice.
Seriously, if you could shrink down and fly inside a grain of salt, you'd see this incredible, repeating grid of positive and negative ions all locked in place, and that powerful electrostatic attraction is what holds it all together so tightly. It's the reason salt is a hard, stable crystal you can actually hold.
But then, what happens when you stir that salt into a glass of water and it just vanishes? That process is called dissociation. The water molecules are actually strong enough to come in, surround those ions, and pull the whole crystal lattice apart. The salt is still there, it's just broken up into its individual ions floating around.
So let's bring this all together. We've talked about atoms giving, taking, and sharing. But why should we care? What's the big deal? Here's the bottom line. The type of bond an atom makes determines what stuff is like in the real world. That give-and-take ionic bond in salt creates a strong, rigid structure, which is why salt is a solid crystal. But the teamwork of covalent bonds in water creates little individual molecules that can flow and slide past each other, which is why water is a liquid. The tiny, invisible bond determines the big, visible world. It's that simple.
And that leaves us with one last question to think about. We've seen how these invisible forces build the salt in your shaker and the water in your glass. So, next time you look around, just wonder, what other invisible bonds are holding your world together right now?